Please subscribe to support the channel. What if the thing that blows up our neat solar system story has been here the whole time and we almost didn't notice it? You're not near Pluto, you're way beyond it, about 71 astronomical units from the Sun. That's 71 times farther out than Earth. Neptune is back at 30 AU. The main Kuiper belt is mostly over by 50 AU. Out here, you're in empty, cold territory, where the Sun is just a sharp star, and almost nothing moves fast. In that emptiness, there is a single icy body, maybe 220 to 380 kilometers across. It is unimaginably faint, barely crawling against the background stars. And it has a name now, officially 2023 KQ14, informally Ammonite. This is not a cute side quest object. This is a warning light. Because Ammonite is not just another thing past Neptune. It is a direct challenge to how we think the outer solar system is built. Every number that describes its orbit says the same thing. Your model is incomplete. We are used to new space rocks being interesting, but harmless. This one is not harmless. This one reaches into the foundations, how the planets formed, whether there is a hidden giant planet, what happened to the Sun in its first few 100 million years, and quietly says, you got something wrong. So why does this single ice ball carry that much weight? Because Ammonite just joined one of the rarest clubs in planetary science. Out of the huge population of trans-Neptunian objects, out of all the icy leftovers and scattered bodies, we only know 4 that live this far out and this detached from the big planets. 4. That's basically nothing. That's not a population, that's a set of clues. The first is Sedna, found in 2003, the original freak. Perihelion around 76 AU, orbits so huge it takes more than 11,000 years to loop the Sun once. The second is 2012 VP113. The third, 541-1132, Leleākūhonua, with an orbit so stretched it spends most of its life unbelievably far away. And now, Ammonite, 4th member of the sednoid group. Sednoid isn't a pretty branding term. It's a hard dynamical label. To qualify, your closest distance to the Sun, your perihelion, has to be beyond about 60 AU, and your semi-major axis, basically half the long axis of your elliptical orbit, has to be greater than 200 AU. In plain language, you do not come close enough to the Sun for Neptune's gravity to kick you around. You live outside Neptune's reach. You are detached. That matters because if Neptune cannot shape your orbit, then something else did, and not gently. To raise a body's perihelion that high and leave it on a stable, long-term orbit, you need serious gravitational violence early in the solar system's history. Ammonite fits the sednoid criteria. It is now part of that tiny, dangerous dataset, and that instantly turns it from random new rock into new constraint on everything. But distance alone isn't the scary part. The time scale is. How long does a year last on this thing? On Earth, 1 year is 365 days. Basic. On Ammonite, 1 year is roughly 3,998 Earth years. One orbit around the Sun takes almost 4 millennia. Here's the shape of that path in simple terms. At perihelion, its closest point, Ammonite comes into about 65.9 AU from the Sun. At aphelion, the farthest point, it reaches around 438 AU. Its orbit has an eccentricity of about 0.74. That means the ellipse is very stretched, and an inclination of about 11 degrees compared to the main planetary plane. Put bluntly, this thing spends almost all of its life in extreme darkness, at extreme distance, moving on a long, thin track that barely brushes the inner edge of the inner Oort Cloud zone. Now, here's the part that should make you feel how fragile our discovery era really is. We're seeing Ammonite now only because we happen to arrive at the one tiny slice of its orbit where it is near perihelion and barely bright enough to detect. For the next few decades, it will be as bright as it ever gets, still at around 25th magnitude, which is far beyond what you can see with your eyes or a normal telescope. After that, it drifts outward, fades, and for thousands of years, it will effectively vanish from human reach. Every person who has ever lived, and everyone alive now, fits inside a microscopic fraction of one Ammonite year. Our entire technological civilization is a tiny glitch on its orbital timeline, yet we happened to arrive at the exact moment it was close enough to spot. That coincidence is what turns this into a high-tension story. We got one shot, we caught it, and the orbit we measured is not comforting. Because here's the real hit. The direction of that orbit attacks the Planet 9 idea directly. When you draw orbits, you don't just care how big they are, you care where they point. Every ellipse has a long axis. The closest point to the Sun, the perihelion, sits on one end of that axis. The direction of that point in space is measured by an angle called the longitude of perihelion. Now, look at the first three sednoids. Sedna, 2012, VP 113. They don't just have high perihelions. Their longitudes of perihelion all bunched in roughly the same region of space, between about 0 and 90 degrees. That should not happen if only the known giant planets are in play. Over hundreds of millions or billions of years, the tugs from Jupiter, Saturn, Uranus, and Neptune should make those angles spread out like random spins of a wheel. Instead of random, we saw a cluster. So scientists did the obvious, dangerous thing. They proposed a new planet, a big one, a super Earth, possibly 5 to 10 times the mass of Earth, orbiting somewhere between a few hundred and maybe 600 AU. Its gravity could herd a group of distant objects into a preferred orientation, creating exactly that cluster in longitude of perihelion. That idea became Planet 9, not a joke, a serious working hypothesis. Simulations showed it could explain several odd patterns in the orbits of extreme trans-Neptunian objects. For a while, Planet 9 was the leading explanation. Ammonite walks in and flips the table. Its longitude of perihelion is about 271 degrees. That is not a bit off. That is roughly opposite the others. On a diagram of orbits, you'd have 3 long ellipses pointing one way and Ammonite pointing into the other side of the sky. So the logic chain now looks like this. If Planet 9 exists and controls these orbits, why is one of the cleanest new sednoids flat out anti-aligned? If Ammonite is stable on that orbit for billions of years, how can a single shepherd planet be keeping a tight cluster and also allowing this rebel to sit safely flipped around? The result is brutal. Either Planet 9 is much farther out and stranger than we thought, or the original Planet 9 argument is breaking. One path says, the hidden planet is real, but we underestimated it. Its orbit might have a semi-major axis closer to 500 AU or more, making it dimmer, slower, and harder to ever detect. It would also mean we need to rebuild all our models around that harsher configuration. The other path says there is no long-lived Planet 9. The clustering we saw is the fading scar of a violent event in the early solar system, a rogue planet that was ejected, a close stellar flyby, or something in the sun's birth cluster. And Ammonite is the object that exposes that truth. The neat Planet 9 story collapses, and we're back to a messier, more chaotic origin. Either way, you lose the simple, clean version of the outer solar system. Ammonite kills that comfort. So you are not watching "We found another tiny world." You are watching the outer solar system's fossil record suddenly gain a new piece that does not fit the puzzle we thought we had solved. What exactly is this sednoid category that 4 objects can shake the entire structure of our planetary system? What kind of object is so rare that 4 of them can threaten the entire story of the solar system? Let's pin this down clearly. What even is a sednoid? Start with the prototype, Sedna, discovered in 2003. Perihelion, its closest distance to the Sun, is about 76 astronomical units. Remember, Neptune orbits at around 30 AU. Sedna never even gets close. Its semi-major axis, the size of its orbit, is roughly 506 AU. Its aphelion, the farthest point, is close to 937 AU. The orbit is extremely stretched, with an eccentricity of about 0.85, and the orbital period? Around 11,400 years for one trip around the Sun. If Sedna celebrated a birthday every orbit, human civilization would not last long enough to see even a tiny fraction of them. That is not a normal trans-Neptunian object. That is a body that lives in a different regime. Neptune cannot grab it. Jupiter cannot grab it. The usual planetary chaos in the outer solar system does not explain this path. Sedna looks like it was placed there by an earlier, more violent event and then left alone for billions of years. That's why astronomers started calling it a fossil record of the early solar system. This is not poetic branding. It is a literal claim. The orbit itself has survived mostly unchanged since the system's early restructuring. So, how do we generalize that weirdness into a category? Sednoid is a cold technical label. It says, this is a trans-Neptunian object with perihelion greater than about 60 AU and semi-major axis larger than about 200 AU. 2 simple cuts. If you do not cross inside 60 AU, you never get close enough for Neptune's gravity to dominate your long-term orbit. If your semi-major axis is above 200 AU, your orbit is huge and slow, so the usual planetary stirring takes a very long time to do anything. Put together, those conditions mean you live on a big, distant, detached orbit that the known planets cannot easily sculpt. These bodies live beyond the effective reach of the main planetary system. They are detached. They are not part of the Kuiper Belt proper. They are not the standard scattered objects still being kicked around by Neptune today. Their orbits are the leftover signature of whatever forced them outward and locked them there. When you look at a sednoid's orbit, you are not reading today's solar system. You are reading what hit it early on when the Sun was still in a crowded birth environment or being disturbed by extra planets. Now here's the punch in the gut. As of 2025, we only know 4 of these things. Sedna, object number 90377, 2012 VP113, 541132 Leleākūhonua, discovered in 2015, and now 2023 KQ14 Ammonite. That's it. 4 confirmed sednoids. We are trying to reconstruct a whole dynamical environment, an entire hidden region of space from 4 data points. That is insane. That is not a small sample. That is a giant warning that we are almost blind out there. We are seeing the brightest, luckiest, nearest few members of what is probably a massive hidden population. Every survey bias works against us. These objects are only detectable near perihelion, only if they're not extremely dark, only if they happen to be in the part of the sky we are scanning. But even with just 3 sednoids at first, there was already something deeply wrong, and it had nothing to do with how far away they were. It had to do with which way their orbits pointed. Take those 3 original sednoids, draw their orbits in space. You don't just get 3 random skinny ellipses at random angles. They're long axes, measured by a quantity called the longitude of perihelion, all landed in roughly the same quadrant, between about 0 and 90 degrees. They were clustered. That should not happen if the only major players are the known giant planets. Over hundreds of millions of years, gravitational tugs from Jupiter, Saturn, Uranus, and Neptune should make those longitudes drift and spread out, randomize them. After billions of years, you expect those angles to look scattered, not packed together. Yet they were packed. When you run dynamical models with only the known planets, That kind of tight alignment is statistically unlikely. You can get it by chance, but not often. So you either accuse the data or you accept that something big is missing. So theorists did the obvious high-risk move. They added a new planet. They proposed Planet 9, a super-Earth in the outer solar system, maybe 5 to 10 Earth masses, semi-major axis somewhere around 250 to 600 AU, far beyond Neptune. Its gravity, acting over billions of years, could trap a group of distant objects into a tight cluster of longitudes of perihelion. Simulations supported it. For a while, this was the leading explanation, a hidden giant planet bending orbits we can see, even if we haven't seen the planet. It was not fringe. It was a serious, testable model. Find more objects, check if the pattern holds. Enter Ammonite, and the pattern cracks. Ammonite easily hits the sednoid distance marks, perihelion around 65.9 AU, and semi-major axis about 252 AU. It is absolutely a member of the same detached family. But when you calculate its longitude of perihelion, you do not get a value in that 0 to 90 degree cluster. You get roughly 271 degrees. That is on the other side of the sky, anti-aligned with the others. This is not a cosmetic detail. This is the core geometry. If the first 3 sednoids pointed one way and the new one points the other, the simple picture, one unseen planet neatly herding them, is in trouble. Either Planet 9 is much farther and stranger than the early models assumed, or the original Planet 9 narrative is simply wrong, and the clustering comes from a different, more violent early event. In both cases, our confidence takes a direct hit. So here's the brutal version. The 4th member of the sednoid family is also the one that might blow up the family theory. The club just gained a new member, and that member immediately challenged the entire reason the club mattered. And that raises a new, harder question. If these 4 objects are this rare, this faint, and this important, how did we even manage to find Ammonite at all? What kind of observing and image processing arms race do you need just to notice a single pixel moving at the edge of the solar system? How do you even find something that is, for all practical purposes, almost invisible? From Earth, Ammonite has an apparent magnitude of about 25.4. Let's be blunt, that is brutal. Your eyes top out around magnitude 6. A good amateur telescope might get you to 14 or 15 visually, maybe deeper with long exposures and clever tricks. Magnitude 25.4 is millions times fainter than what you can ever see directly. You're in the regime where single photons hitting the detector actually matter. If a few photons don't arrive, the object just doesn't exist in your data. At that level, the universe is basically trying to erase this thing. The sky background, detector noise, cosmic rays, faint galaxies, everything is louder than Ammonite. You don't see it in any normal sense. If you tried to look for it by eye on a single image, it would be indistinguishable from random specks. So how did anyone pull this off? The answer is that this is not a casual observation. This is a full-on hunt. The discovery came from a dedicated project, Fossil, Formation of the Outer Solar System and Icy Legacy. They used the 8.2-meter Subaru telescope on Mauna Kea with its Hyper Supreme Cam, one of the widest, deepest optical cameras on any big telescope. Here's the basic idea. In 2023, the Fossil team scanned specific patches of sky in March, May, and August. They didn't just take one picture and leave. They took repeated images of the same fields over hours and over months, and then combed through them, looking for anything that moved just a tiny bit between frames. Everything fixed, stars, distant galaxies, stays in the same place. Solar system objects shift slowly as they orbit the sun and as Earth moves around its own orbit. If you line up your images on the stars and look for dots that shift a little between exposures, those are your targets. That's the classic moving object search. But at magnitude 25, that simple approach hits a wall. Ammonite is so faint, you don't clearly see it in any single raw exposure. It's buried in the noise.
If you scroll through the frames, you don't get a nice blinking dot. You get nothing reliable. So the team uses something more aggressive: shift and stack. Instead of asking, "Do I see a dot in each image?" you assume a possible path across the sky, how fast the object might be moving and in what direction, and then you digitally shift each individual exposure so that a hypothetical object following that path would line up. Then you stack those shifted images together. If you guessed the motion correctly, a real moving object's signal adds up image after image. Noise, which is random, tends to cancel out when averaged. The result is that a dot that was invisible in single frames emerges as a faint but statistically real signal in the combined stack. If you guessed the motion wrong, nothing appears. So you try many possible motions. This is raw computational force applied to the sky. It's not romantic. It's pattern extraction at the edge of what the hardware can handle. This is how deep surveys like Fossil drag distant trans-Neptunian objects out of the static. You're not catching bright planets. You're pulling near-invisible debris out of a sea of noise, one statistical whisper at a time. Once Fossil flagged Ammonite as a real moving object at about 71 AU, the next problem was not, is it real? The next problem was, what is its orbit? Because the orbit is the whole story. Distance, perihelion, semi-major axis, that's where the sednoid status lives. But with only a short observational arc from 2023, the orbit would be very uncertain. If you only watch a car for 1 second, you can't reconstruct its entire road trip. You need a longer trail. So the team did what modern astronomy does best. They went backwards in time through the archives. First, they searched images taken by the Dark Energy Camera, DECam, on the Blanco 4-meter telescope in Chile. DECam is designed for deep, wide-field imaging, mostly for cosmology, but it sees everything in its field, including solar system objects. They found pre-discovery appearances of Ammonite in DECam data from 2014 and 2021. Then they dug even further back into data from Kitt Peak from 2005. Again, at the time, no one knew that faint, slow-moving point was Ammonite. It was just one more unnoticed object in a huge data set. Only after you have a preliminary orbit can you predict where the object should have been years earlier and search those images. Finally, they added new follow-up observations from the Canadian-France-Hawaii Telescope, CFHT, in 2024. Those fresh positions pin down where the object is now with high precision. Put all of that together and you get a 19-year observation arc: 2005, 2014, 2021, 2023, 2024. That long baseline radically shrinks the uncertainties in the orbit. Now you can say something solid about its perihelion, its semi-major axis, its eccentricity, its inclination. Only with that many years of data does it become clear. This is not a random scattered object. It's a genuine sednoid. Without that archive work, you would have a blurry, weak orbit and no right to make big claims. With it, you're allowed to say the scary thing. Ammonite is detached, stable, and dynamically part of the sednoid group that threatens the Planet 9 story. So where does that leave you, the viewer, with your telescope in the backyard? Let's be direct. You will never see Ammonite from home. No filter, no stacking app, no lucky night will bridge that gap. Even many professional telescopes cannot detect it in a single exposure. You need huge mirrors, ultra-sensitive detectors, perfectly dark skies, and long integrations over multiple nights to pull it out. And even then, it comes out as a faint smudge in a processed stack. That's the punchline. It took some of the most powerful survey hardware on Earth, some of the best image processing techniques we have, and nearly 2 decades of scattered data to barely confirm the existence of a world hundreds of kilometers wide in our own solar system. If that is what it costs to see one object like this, Imagine how many more are out there that we simply cannot reach yet. Ammonite isn't just a discovery, it's a loud reminder of how blind we still are beyond Neptune. And that brings us to the next critical step. Now that we've found it and pinned down its position over 19 years, what does the actual orbit look like when you write out the numbers? How exactly does this 4,000-year path break the pattern we thought we understood? How much damage can a single orbit do to our picture of the solar system? Let's stop talking in general terms and look at the raw numbers, because this is where Ammonite stops being interesting and starts being dangerous. Here's the orbit stripped down. Semi-major axis about 252 astronomical units. That's the basic size of the ellipse. Perihelion, the closest point to the Sun, about 65.9 AU. Aphelion, the farthest point to the Sun, around 438 AU. Eccentricity, about 0.7385, so this is a very stretched path, not a neat circle. Inclination, about 11 degrees, so it's a bit tilted relative to the main planetary plane, but not wildly so. Orbital period, about 3,998 years. Call it a 4,000-year year. Put that next to Neptune. Neptune sits at roughly 30 AU. Ammonite never comes closer than about 66 AU. That is more than double Neptune's distance at its closest point, and a huge fraction of a light day at its farthest. On any solar system map, its orbit is a long, thin loop, far outside the region we actually understand. We are not talking about a small tweak beyond Pluto. We are talking about a separate zone where our observational coverage is terrible and our models are shaky. Now the crucial part. This is not some unstable temporary orbit that will be ripped apart. Because Ammonite never comes inside that 66 AU boundary, it stays well beyond Neptune's gravitational reach. When you run full N-body simulations with the known giant planets, Ammonite's orbit holds together for billions of years. You can integrate it over the age of the solar system, forward and backward, and it stays detached and stable. That matters. If the orbit were chaotic or short-lived, you could shrug and say, random scattering put it here recently, no big deal. But a dynamically stable orbit over 4.5 billion years is a different thing. It means this configuration is not a fluke. It has survived. It is a fossil orbit. So the basic picture is a 4,000-year, high eccentricity, 252 AU wide ellipse inclined by about 11 degrees that never gets near Neptune and does not fall apart over the lifetime of the solar system. That alone puts it in the sednoid class. But that is not the part that attacks Planet 9. The real hit is which way the orbit points. Every ellipse in space has a direction. The closest point, the perihelion, is not somewhere. It's at a specific angle around the Sun. We describe that with the longitude of perihelion, usually written as the symbol, Warve. Think of it as the bearing that tells you where the ellipse points. For the first three sednoids, that angle is clustered. Their longitudes of perihelion lie between about 0 and 90 degrees. Three different objects, independent discoveries, all with long axes pointing into roughly the same quadrant of space. That clustering is the original reason Planet 9 became a serious idea. It looked like the signature of a common shepherd. Now put Ammonite into the same coordinate system. Its longitude of perihelion is about 271 degrees. That is not just different. That is almost opposite. On an orbit diagram, if you draw all four sednoids projected into the same plane, you get three long loops leaning one way, and then Ammonite's ellipse swung around, pointing into the other side of the sky. You cannot sweep that under the rug. If the whole point of Planet 9 was to explain the clustering of these longitudes, the arrival of a clean, detached sednoid with an anti-aligned perihelion is a direct challenge. You now have to explain both the cluster and the rebel with the same physics. That is not optional. That is the test. So what do? You run the clock. Numerical models take the current orbits of the four sednoids and integrate them backward for billions of years under different assumptions. No magic, just gravity and time. The idea is simple.
If you start from what we see today and rewind, do their longitudes of perihelion ever line up in the past, or are they always scattered? In the models without Planet 9, but with the known giant planets and the standard galactic tidal background, something interesting happens. When you push back to about 4.2 billion years ago, the longitudes of perihelion of all four sednoids become strongly clustered, not kind of close, tight. The calculations show that the chance of getting that kind of alignment by pure randomness is very low, with confidence above 97% that the clustering is real, not a statistical accident. Then you move forward again from that early time to the present, the orbits precess. That just means their long axes slowly rotate under the combined gravitational influences. Over billions of years, that rotation spreads the longitudes out. What was once a tight group becomes a wider spread. Three objects end up still relatively close in angle. One, Ammonite, ends up drifting to the opposite side of the sky. This immediately changes how you interpret the rebel orbit. It is not just off pattern. In this picture, it is the object that shows you how far the precession has gone. It carries both phases of the story. It was part of the original aligned configuration 4.2 billion years ago, and it now sits far from that direction because its orbit has had more time or more sensitivity to drift. The other three are in between. Together, the four orbits trace the evolution from an initial clustered state to the current mixed state. If that early clustering is real, you are forced to one conclusion. Something in the early solar system pushed these bodies into that aligned configuration. Not the slow, weak tug of the galactic tide. That is too gentle to create a sharp cluster on its own. You need a strong event or a massive perturber. The candidates are ugly. A rogue planet that used to orbit farther out and was later ejected. A close pass by another star while the sun was still in a dense birth cluster. Or some combination of extra planets and stellar encounters. Whatever did it left almost no direct trace we can see today. No obvious ninth planet in a clean orbit, no surviving star nearby that we can point to and say, that one did it. What we have instead are these four frozen orbits: Sedna, 2012 VP113, Leleākūhonua, and Ammonite. And within that set, Ammonite is crucial because it is both a member of the group and the outlier in orientation. That is why this object is so dangerous to our old story. It does not let you keep the simple Planet 9 explanation without heavy modification. It pushes you toward a more violent early history for the solar system, and toward the idea that a lot of the real action happened in a time window we will never directly observe. And this raises the next big question you have to confront. If the orbit is this extreme and this stable and this telling, what kind of physical world are we actually talking about? What does a 220 to 380 kilometer object sitting at 70 AU in deep freeze look like in terms of size, color, composition, and surface? How much can we really say when all we see is a faint point of light? How do you describe a world you will never see as more than a single pixel? Right now, Ammonite is not a tiny disk. It's not a sphere. It's not even a blur. On our images, it's a point. That's it. One unresolved dot of light. So how do you get anything out of that? You use brightness and reflectivity. We know how much light Ammonite sends us at its distance. That's its apparent brightness. But that brightness depends on two things: how big it is and how reflective its surface is. A big dark object and a smaller bright object can look the same. So astronomers assume a plausible range of reflectivity, or albedo. For outer solar system ices, a typical range is between 0.05 and 0.15. That means it reflects about 5 to 15% of the sunlight that hits it. Plug that into the standard formulas along with the observed brightness, and you get an estimated diameter somewhere between about 220 and 380 kilometers.
That's not tiny. That puts Ammonite in the same general size class as some classical dwarf planet candidates. It's smaller than Sedna or Pluto, but it's not a random pebble. It's a serious, mid-sized icy world. It is big enough that gravity will have rounded it at least somewhat. It has real geology, not just rock with a number. But the classification is not official.
No one has stamped dwarf planet on it yet, because to do that properly, you'd want better constraints on size and shape. Still, you can say bluntly, this is not debris. This is a substantial object. Knowing the size is one thing. Next question, what does the surface look like? Astronomers don't see features, but they do measure color. They take images through different filters. For example, G, greenish, R, red, I, near infrared, and compare how bright the object is in each band. For Ammonite, the color indices come out around G-R approximately 0.87 and R-I approximately 0.36. In normal language, it's moderately red, not the most extreme red in the outer solar system, but clearly shifted toward redder wavelengths compared to a neutral sunlight color. That puts it in line with many trans-Neptunian objects and some of the other sednoids. What does red actually mean out there? It doesn't mean iron rust. It usually means the surface is covered in complex organic material called tholins. These form when ultraviolet light and charged particles from the sun and cosmic rays hit ices like methane and methanol over billions of years. The radiation breaks molecules apart and rebuilds them into heavier, more complex organics that tend to be dark and reddish. So that moderate red color tells you the surface is old, processed, and coated in radiation-baked material. This is not a fresh, clean ice ball. It has been sitting out there, getting cooked by space basically since the early days of the solar system. Fine, you know roughly how big it is, and that it's reddish. Next question, how is it spinning? Is it a tumbling chunk or a quiet, slowly rotating body? To answer that, you watch how its brightness changes with time. If the object is very elongated or has big contrast patches, bright and dark regions, then as it rotates, the light we see rises and falls in a repeating pattern. That's a light curve. In 2025, astronomers used the Magellan telescopes to do follow-up observations of Ammonite, specifically looking for these brightness changes. They did not see strong variations. No big spikes, no deep dips, nothing screaming extreme shape or wild rotation. That result suggests a couple of things. One, Ammonite is probably not a dramatically elongated object. It may be more rounded, closer to a spheroid. Two, its rotation might be relatively slow, or our viewing angle could be near its rotational pole, which would also minimize observed changes. Either way, this is not a chaotic tumbler. This world is quiet in its spin signature. So, we have a mid-sized, moderately red, apparently fairly regular ice ball on a 4,000-year orbit far beyond Neptune. But that's just the surface. What about the inside? At 220 to 380 kilometers across, you are in the regime of standard icy bodies. The basic picture is a mixture of water ice and rock, with maybe a bit of other frozen volatiles near the surface. Gravity's strong enough to compress it, but not strong enough to guarantee a fully differentiated interior like a big planet. If Ammonite is anything like Sedna and other distant objects, its surface could host nitrogen ice, methane, methanol, and tholin-rich material. Underneath, you'd expect water ice mixed with silicate rock. Maybe some internal porosity, maybe a history of slow radioactive heating early on. But here's the key. We don't have a detailed spectrum yet. We don't have high-resolution lines that tell us exactly which ices are present. That means the interior and detailed surface composition are still educated guesses. But they're not wild guesses. They're based on what we see in similar bodies. Right now, we're at the stage where we can say it is a standard outer solar system ice rock mix with a processed reddish surface. The next big step is to get real spectra and confirm or break that picture. That's the race now. We found the object, we've measured its orbit. The next move is to steal as much compositional information as we can from its faint light before it drifts farther away and becomes even harder to study. And then there's the temperature. How cold is a fossil like this, sitting around 70 AU from the sun? At that distance, the sun's energy is extremely weak. The equilibrium temperature, the balance point between sunlight absorbed and heat radiated away, is only a few tens of Kelvin. You're looking at something like minus 230 degrees Celsius. This is deep freeze. Water ice is rock hard. Most chemistry is effectively shut down. Thermal processes are slow to the point of being negligible on human timescales. That is exactly why these sednoids are so valuable. They sit in conditions where everything is slowed to a crawl. Surfaces evolve, but they evolve over billions of years under low temperatures and steady radiation, not rapid melting and refreezing. Interiors, if they ever had liquid layers, would have frozen long ago. You are looking at a body that has barely changed structurally since it was placed on its current orbit. So now you have a clearer picture. Ammonite is a mid-sized, moderately red, radiation-processed ice rock body, quietly rotating, frozen to extreme temperatures, riding a stable 4,000-year orbit far beyond Neptune. It is not spectacular visually, but it is brutally informative. And that leads to the next hard question. Where exactly does this thing sit in the larger structure of the solar system? It's not a standard Kuiper Belt object. It's not a classic distant Oort Cloud comet. It lives in a gray zone we barely understand, a region that might be the key to the entire architecture. What do you even call a place that's too far out to be the Kuiper Belt, but too close in to be the classic Oort Cloud? That's where Ammonite lives, in the no man's land. Start simple. Neptune orbits at about 30 astronomical units. The main Kuiper Belt, the quote-unquote standard ring of icy bodies, runs from just beyond Neptune out to about 50 AU. That's the zone of Pluto, Makemake, Haumea, and a whole zoo of trans-Neptunian objects. Ammonite's closest approach to the Sun is about 65.9 AU. That's almost 16 AU beyond the outer edge of the Kuiper Belt. It doesn't just graze past the Kuiper Belt, it clears it by a huge distance. And at the far end of its orbit, around 438 AU, it's pushing in toward the territory that many dynamical models link to the so-called inner Oort Cloud or Hills Cloud, a region that really kicks in around 1,000 to 10,000 AU. So Ammonite is not a classic Kuiper Belt object, and it's not a full Oort Cloud comet either. It's sitting on the inner fringe of that deeper structure, right in the transition zone. Close enough that we can just barely detect it, far enough that it's already part of the structure that feeds the true Oort Cloud. That position is not an accident. It tells you exactly what kind of object we're dealing with. In dynamical language, sednoids belong to a larger group called detached objects. That label is very literal. Detached objects are high perihelion trans-Neptunian objects that are not currently under Neptune's control. Their closest approach is so far out that Neptune's gravity can't significantly change their orbits on reasonable timescales. Sednoids are the extreme end of that detached category. Perihelion greater than about 60 AU, semi-major axis greater than 200 AU. They're the detached of the detached.
Why does that matter? Because if Neptune isn't driving their orbits today, then their current paths were carved by something that acted earlier, harder, or farther out. Their orbital shapes, the perihelion distance, the eccentricity, the inclination, the direction they point, are essentially the record of that event. In that sense, detached objects act like seismographs. You don't see the original quake, but you read the wiggles in the trace and reconstruct what hit the system. Ammonite's orbit is one of those traces. High perihelion, big semi-major axis, stable over billions of years. That is a signature of an old, strong disturbance that shoved it outward and then left it stranded beyond Neptune's reach. Now here's the truly uncomfortable part. If we found a few of these things, how many are actually out there? Leleākūhonua, the third sednoid, was already a major warning signal. Its discovery implied that there might be something like 2 million inner Oort Cloud objects larger than about 40 kilometers in diameter. 2 million. That hidden population, if it exists at that scale, would have a combined mass roughly comparable to Pluto's. Think about what that means. We have mapped the major planets. We have cataloged hundreds of thousands of asteroids. We have found thousands of Kuiper Belt objects. And beyond that, there could be a swarm of millions of inner Oort Cloud bodies, and we have direct evidence for 4 sednoids. Sedna, 2012 DP113, Leleākūhonua, Ammonite. 4 detections out of a possible millions. That's not a weird minority. We are almost completely blind, and we just happen to have bumped into the brightest, nearest few. Ammonite is one data point in that ocean, but each new sednoid isn't just one more. It reshapes how we estimate the size and structure of the inner Oort Cloud. The fact that Ammonite shows up in our limited surveys means the unseen background is massive. You do not get 4 of these in the tiny part of the sky we've searched unless there is a huge reservoir behind them. So what has been shaping that reservoir for billions of years? At hundreds of astronomical units from the Sun, the game changes.
Inside the planetary region, the main gravitational players are the Sun and the known planets. Beyond a certain distance, something else joins the game: the galaxy itself. The Milky Way's gravitational field exerts a slow, steady pull, a galactic tide, on distant solar system bodies. Over giga-year timescales, that tide can gradually change orbits, lifting perihelion, stretching semi-major axes, altering inclinations. It doesn't slam objects around like a close planetary encounter, but it can steadily torque them. On top of that, the Sun does not live in a vacuum. Over billions of years, other stars pass nearby. Most of those passes are very distant and weak, but occasionally one comes close enough, maybe a few thousand AU, maybe even a few hundred AU back when the Sun was still in its birth cluster, to give the outer reservoirs of icy bodies a serious kick. Those stellar flybys can yank orbits outward, tilt them, or change their perihelion. Ammonite's entire life has played out in that regime. For 4.5 billion years, its long, stable orbit has been evolving under the combination of the Sun's pull, the distant tug of the planets, the galactic tide, and the accumulated effect of whatever stellar encounters the solar system has experienced. It's been sitting in the crossfire of slow, large-scale forces that we can only model statistically. That's the part that should feel heavy. Ammonite is not just far. It's in the zone where the galaxy and ancient stellar neighbors start to rival the known planets as shapers of orbits. It's in the region where the solar system stops being a close-knit family and starts being just one system embedded in the larger gravitational field of the Milky Way. So when you look at Ammonite's orbit, you're not just learning about Neptune and a hypothetical planet 9. You're reading the influence of the Sun's birth cluster, past stellar flybys, and the galaxy's slow grip. One small object carrying the imprint of all of that. And that leads straight into the next clash. If the galaxy, passing stars, and early violent events are all on the table, where does that leave the Planet 9 idea? Does it weaken it? Force it into a narrower corner? Or does it point instead to a completely different kind of origin story? Rogue planets, ejected giants, and flybys that rewrote the outer solar system before it even settled. What happens when a new object walks in and points straight at the weak spot in your favorite theory? Planet 9 was not born as a wild guess. It came from a very specific pattern. Astronomers noticed that a group of extreme trans-Neptunian objects, including the sednoids, had perihelion that lined up in space. Their long axes pointed in roughly the same direction, and their orbital tilts were similar. That should not be normal if only the known giant planets are running the show. Over billions of years, those angles should get scrambled. So people did the obvious thing. They tried to add a new planet into the simulations. Give it a mass of maybe 5 to 10 Earths. Put it on a distant, elongated orbit, somewhere around 400 to 800 astronomical units from the Sun. Let it run in the code for billions of years. And it worked. The extra gravity from that distant super-Earth could trap a group of far-off objects into a cluster configuration. Their perihelion would line up, their orbital tilts would fall into a band. The pattern we saw in the data came out naturally. That was the original Planet 9 argument. Not a picture, not a direct detection, but a clean chain, weird clustering in real orbits, plus a plausible unseen planet, plus simulations that match the pattern. It was simple, powerful, and hard to ignore. For almost a decade, Planet 9 was the main way to explain why the outer solar system did not look random. Then Ammonite shows up and punches that simplicity in the face. Ammonite is a textbook sednoid on distance. Perihelion around 65.9 AU. Semi-major axis around 252 AU. Giant 4,000-year orbit, detached from Neptune. It fits every distance cut used to define the group. But when you measure its longitude of perihelion, you do not get a value near the original cluster between 0 and 90 degrees. You get around 271 degrees. That is almost on the opposite side of the Sun. This is the problem. A single shepherd planet, like Planet 9, is supposed to herd the perihelia of these distant objects into a restricted zone. That is the whole point. Ammonite lives in the same dynamical class, but points the other way. You now have one of two choices. Either the Planet 9 model is incomplete in a serious way, or the clustering was telling you something else from the beginning. Is that the death blow? Not quite, but it is a hard crack in the armor. Dynamics people did what they always do. They threw Ammonite into the simulations and pushed the system through billions of years. The logic was aggressive and simple. If Planet 9 exists, and if Ammonite has been sitting on a stable orbit for more than 1 billion years, what does that force Planet 9 to look like? The answer is not comforting. To keep Ammonite stable while still explaining the other clustered objects, Planet 9 probably has to orbit farther out than many early versions suggested. You're no longer comfortable at 400 AU. You start needing a semi-major axis more like 500 AU or more, with tuned eccentricity and inclination. The allowed parameter space shrinks and shifts outward. That makes the planet harder to find. A more distant Planet 9 would be dimmer, slower against the background stars, and deeper into the worst region of the sky for ground-based surveys. You can still keep the idea alive, but you are pushing it into a corner where it is both more difficult to detect and more fine-tuned. At the same time, another option has been getting stronger: no Planet 9 at all. Once you include Ammonite and the other sednoids in models without Planet 9, a different picture appears. You take their present-day orbits, run them backward with just the known planets and the galaxy's tide and realistic past stellar encounters, and you find that around 4.2 billion years ago, the longitudes of perihelion of all 4 sednoids were strongly clustered. Then, over time, their orbits precess. Their perihelia slowly rotate around the sun. The tight cluster spreads. In that scenario, you don't need a long-lived Planet 9 to keep them aligned forever. You need a strong event early on, a rogue planet that used to be out there, a close pass by another star when the sun was still in a dense cluster, or some violent rearrangement of the giant planets. That early event pushes a group of bodies into aligned, high perihelion, large semi-major axis orbits. Then the alignment decays over billions of years. In this version, Ammonite's weird angle is not a bug. It is exactly what you expect if the original cluster is fading. 3 sednoids still lie roughly together. 1 has drifted far. The spread itself becomes the data. Ammonite is the piece that says, yes, the system is evolving away from that original alignment. So now you have 2 clashing stories on the table. Story 1, Planet 9 is real, but farther out and more constrained than we thought. It is still sculpting the orbits today, still maintaining a structure in the distant population. Ammonite forces you to push the planet into a more extreme orbit and adjust the details, but the core idea survives. Story 2, there is no Planet 9 now. The clustering is a fossil from an early violent event. The sednoids, including Ammonite, remember that event in their orbits. The fact that one of them is anti-aligned today is direct evidence that the early pattern has been smeared out by precession, not preserved by a shepherd. Neither story is comfortable. One demands a hidden super-Earth we have not seen despite years of targeted searches. The other demands a strong ancient disturbance, maybe a now ejected planet, maybe a close stellar flyby that rewrote the outer solar system and then left almost no direct trace. Here's the brutal narrative beat. The object that should have strengthened the case for a hidden planet instead opened the door to the possibility that the planet never existed, or existed only briefly and was thrown out into interstellar space long ago. Ammonite does not let you relax into a neat answer. It makes the story darker and more unstable. And that leads directly into the next step. If Planet 9 is no longer the only explanation on the board, what are the other origin stories? What kind of early solar system event is big enough to create a whole population of sednoids, bend their orbits into alignment, and then vanish, leaving only these distant fossils as evidence? What kind of event is violent enough to bend whole swarms of icy worlds into weird high perihelion orbits and then disappear without a trace? If Planet 9 isn't the whole answer, You're left with origin stories that are all brutal in different ways. None of them are gentle. All of them say the early solar system was more dangerous and unstable than our textbooks made it look. First scenario, the rogue planet sculptor. Picture a massive planet, somewhere between Earth and Neptune in size, born in the outer regions of the solar system. Not the nice, compact 8-planet system we see today, but a crowded, messy version with extra giants on stretched-out orbits. That extra planet spends time moving through the region beyond Neptune, scattering icy planetesimals outward. Every close encounter flings bodies to higher eccentricities and larger semi-major axes. Some get thrown inward and destroyed. Some get ejected completely, becoming rogue planets between the stars. But some get pumped into high perihelion, detached orbits, not close enough to the Sun for Neptune to touch anymore, but still bound to the system. Exactly the kind of orbits we see in the sednoids. Simulations back this up. Put a Neptune-mass planet or super-Earth mass planet in the outer system for a while, let it interact with a proto-Kuiper belt and scattered disk, and you naturally create a detached disk of objects with perihelia in the 60 to 80 AU range and large semi-major axes. You get Sedna-like orbits. Then, if that rogue planet later gets ejected by interactions with Jupiter and Saturn or tossed outward to thousands of AU, it vanishes from direct detection. You're left only with the detached population it created. In that story, the sednoids are fingerprints of a missing planet that was real and is now gone. Second scenario, the stellar flyby. When the Sun was young, it did not form alone. It formed in a dense cluster with many other stars packed into a relatively small volume. In that environment, close stellar encounters are not rare. A neighboring star can pass within a few thousand AU, or even a few hundred AU in extreme cases.
If a star comes that close, its gravity can heavily disturb the outer parts of the solar system. It can yank planetesimals outward, raise their perihelia, and create extended, scattered disks in inner Oort Cloud populations. We see this in simulations. Set up a proto-solar system, then send a star past on a realistic orbit with realistic speed, and you get Sedna-like objects as a natural byproduct. In this model, you don't need an extra planet staying around. You need one strong, one-time event early on. A stellar flyby sweeps past, jolts a whole swarm of icy bodies into high perihelion, large semi-major axis orbits, and then leaves forever. The star is long gone now, somewhere else in the galaxy, but the orbits it carved around the Sun stay. Third scenario, captured exiles. This one is more exotic, but still on the table. In a dense young cluster, stars don't just pass by each other, their planet-forming disks can overlap at the edges. When that happens, they can actually swap material. Planetesimals, kilometer-sized building blocks of planets, can be stripped from one star's disk and captured by another's gravity. So some researchers have proposed that sednoids might not be born here at all. They might be captured bodies from another star's outer disk. In this picture, Sedna, 2012 VP113, Leleākūhonua, and Ammonite could be exiles, originally formed around a nearby solar sibling star and stolen by the Sun during a close encounter in the birth cluster. Simulations of this process show that it can produce high perihelion, large semi-major axis orbits that look a lot like what we see. The trade is chaotic, but the end result is a population of distant, detached bodies on strange orbit. Exactly the kind of fossil population we're talking about. Fourth ingredient, the galactic tide slow burn. On top of all that, you have the constant background pull of the Milky Way itself. The galaxy's gravitational field acts on distant solar system objects all the time. Over giga-year timescales, the galactic tide can slowly lift perihelia, stretch orbits, and change inclinations. For the classical Oort Cloud, this tide is a major player. But there's a catch. The galactic tide is slow and smooth. It's good at gradual reshaping. It's not good at creating a sharp, tightly aligned cluster of perihelia like we infer for the sednoids around 4.2 billion years ago. So tides alone don't match the story.
They look more like the background sculptor that takes an already disturbed population and continues to evolve it, not the one-time hammer that created the initial configuration. So how does Ammonite fit into this zoo of possibilities? Ammonite's orbit is stable over billions of years. Its perihelion is high. Its semi-major axis is large. Its orientation, when you run the system backward, lines up with the other sednoids around 4.2 billion years ago. Together, the four sednoids point to a strong early perturbation and then a long period of quiet evolution. That timing is important. The solar system is about 4.5 billion years old. An event around 4.2 billion years ago means something big happened roughly 300 billion years after formation. That's late enough that the main planets were probably already in place, but early enough that extra bodies and star encounters were still possible and messy. If you combine the evidence, the picture that emerges is not a gentle, isolated sun slowly building a neat planetary system. It's a young star in a hostile environment, with extra planets, close stellar neighbors, and the galaxy's tide all interacting, leaving behind a handful of frozen witnesses on extreme orbits. Ammonite strengthens that picture. It doesn't just add one more weird orbit, it locks down the idea that the sednoids once shared a tighter alignment and have since spread. That pattern screams strong early perturbation more than calm, untouched fringe. But that raises a new, uncomfortable question. If this whole story depends on careful orbits, long baselines, and subtle angles, how close did we come to missing it completely? How far back does the observational trail of Ammonite actually go, and how did we piece together that it was special rather than just another faint speck? How close did we come to missing Ammonite completely? Let's walk through the timeline, because this thing was hiding in plain sight for almost 20 years. Start in 2005. No one has heard of Ammonite. No one is looking for sednoids as a defined group. At Kip Peak, wide-field images are being taken for other science, galaxies, large-scale structure, whatever. In those images, there is a faint, barely moving dot amongst thousands of stars. It shifts a tiny bit between exposures, but there are countless faint dots, and nothing about this one screams, "Pay attention." So in 2005, Ammonite is effectively a ghost. It's there, recorded on a CCD, photons captured, coordinates logged, but no one connects the dots. There is no orbit, no object, no name. It's just data. Fast forward to 2014 and 2021. Different telescope, different survey, same story. The dark energy camera, DECam, on the Blanco 4 meter at Cerro Tololo is doing deep imaging for cosmology. It's hunting for dark energy signatures, mapping galaxies and clusters across huge fields. DECam is absurdly sensitive. When it stares at the sky, it also picks up solar system objects as collateral damage. Ammonite passes through those fields. Again, it shows up as a faint dot in 2014. Again in 2021. It moves slightly between exposures, obeying the same slow, distant motion it always has. But at the time, these frames go into the archive. Nobody has a reason yet to dig into that exact patch of sky and ask, is there a distant trans-Neptunian object hiding in here? So the signal sits on disk, invisible in plain sight. This is the brutal reality. The universe is constantly telling us things, and we only understand them when we go back with a specific question. Now, jump to 2023. This is where Ammonite finally gets caught on purpose. The fossil survey, formation of the outer solar system, an icy legacy, is up and running on the Subaru telescope with Hyper Supreme Cam. This is not a casual look. Subaru has an 8.2 meter mirror and a powerful wide-field imager. Fossil is designed to go after exactly the kind of faint distant objects we've been talking about. In March 2023, the team images a field. They come back in May, then again in August. They line up those images and run their moving object detection pipelines. Among the many faint specks, one source at about 71 AU stands out. It moves with a slow rate expected for a very distant trans-Neptunian object. Its brightness matches something a few hundred kilometers across at that distance. The motion is coherent. This is not noise. This is not a galaxy. This is a real distant body in the solar system. At that point, they know this is a new trans-Neptunian object, likely around 70 AU, but the orbit is still fuzzy. With only that year's data, you can't say exactly how far out the aphelion is. You can't pin down the semi-major axis or the precise perihelion distance. You have a direction, a rough distance, a speed, and a magnitude. Enough to get excited, not enough to classify it as a sednoid. So what do? You go digging. Armed with a preliminary orbit from 2023 Subaru data, the team runs pre-covery searches. That means you use the rough orbit to predict where the object should have been in earlier years and check existing images from other telescopes. That's when the Kit Peak 2005 data and the DECam 2014 and 2021 frames suddenly matter. You go into those old images knowing roughly where and how fast to look. You don't scan blindly. You search a tiny area along a predicted track. And there it is, the same faint dot at the right place, moving at the right rate years earlier. Those detections turn from anonymous artifacts into pre-covery points for Ammonite. Now the orbit locks in tighter. You've extended your arc from a single year to almost 2 decades, 2005, 2014, 2021, and 2023. But you're not done. You need fresh, precise positions to clean up the remaining uncertainties. So in July 2024, the Canadian-France-Hawaii telescope comes into play. CFHT adds new measurements with high positional accuracy. These updated coordinates are gold. Combined with all the historical detections, they finally give the orbit enough precision to answer the real question: is this a sednoid? Run the fit, check the parameters. Perihelion, about 65.9 AU. Semi-major axis, greater than 200 AU. Eccentricity, high. Inclination, moderate. The numbers lock in. This is not just another distant object. It satisfies the hard dynamical criteria. At this point, internally, the team knows what they're looking at: a probable 4th sednoid. Now we hit 2025, when this stops being inside baseball and goes public. On April 14, 2025, the Minor Planet Center issues the official circular. The object gets its formal designation, 2023 KQ-14. Observations from different facilities are consolidated, the orbit elements get posted, and the solar system community now has a new distant body on the books. Then, on July 14, 2025, the full discovery paper appears in Nature Astronomy. That's the moment the wider community and the media jump. The paper doesn't just list orbital elements, it lays out the whole story. The 19-year observation arc, the sednoid classification, the statistical arguments about early alignment around 4.2 billion years ago, and the implication that Ammonite's anti-aligned perihelion is a serious problem for simplistic Planet 9 models. Press releases follow from institutions like NAOJ and others. The messaging is blunt. This is a fossil of the early solar system, and it challenges the Planet 9 hypothesis. It's not framed as a fun curiosity. It's framed as evidence with teeth. So, step back and look at the full timeline. 2005. Ammonite is an unnoticed dot in Kit Peak data. 2014, 2021, it's an unnoticed dot in DECam data. 2023, Subaru's fossil survey finally spots it as a moving object at nearly 71 AU. 2024, CFHT tightens the orbit. The sednoid nature becomes clear. 2025, the Minor Planet Center makes it official. Nature Astronomy lays out the implications. The world hears the words 4th sednoid and Planet 9 in trouble in the same breath. This is how close we were to never knowing. If Subaru hadn't run fossil, if no one had gone back through the archives, Ammonite would still just be pixels nobody cared about. The orbit and all its consequences would be invisible. And that raises the next level of tension. If it took this much effort to secure one object's orbit, how do we really test whether it's stable over the full age of the solar system? How do we know this isn't some temporary accident versus a true fossil? To answer that, you have to do something even more extreme. Turn the entire outer solar system into a numerical experiment and watch it evolve for 4.5 billion years inside a computer. How do you prove that an orbit we see today isn't just some recent accident, but a fossil that's been there since the beginning? You can't wait 4.5 billion years and see what happens, so you cheat. You build a time machine in code. To test Ammonite's orbit, you take its current orbital elements and those of the giant planets, Jupiter, Saturn, Uranus, Neptune, and you feed them into an n-body integrator. That's just a simulation that calculates gravity between multiple bodies and updates their positions step by step. No magic, just physics and a lot of computing. Then you hit go. You run the system forward in time for billions of years. You run it backward for billions of years. You flip switches, models with Planet 9, models without Planet 9, models with idealized stellar encounters, models with just the standard background. You push the system from every angle and watch what happens to Ammonite's orbit. The key question is simple and brutal. Does this orbit fall apart or does it survive? The fossil team's results in the no Planet 9 case are clear. Ammonite's orbit is stable over at least 4.5 billion years when you use its best fit current parameters. It does not crash into Neptune. It does not dive inward. It does not get flung away. The perihelion stays high, the semi-major axis stays in the same ballpark, and the overall shape holds. That means this orbit is not some recent fragile configuration that just formed. It's compatible with being there for the entire age of the solar system. In other words, Ammonite behaves like a preserved relic, a survivor. You're not seeing a transient glitch. You're seeing the long-term, durable outcome of whatever brutal event put it there. But stability is only half the story. The other half is, what did things look like before? When you run the system backward with all four sednoids, Sedna, 2012 VP113, Leleākūhonua, and Ammonite, you track how their orbital orientations evolve. Specifically, you watch the longitudes of perihelion, those angles that tell you which way their ellipses point. Today, those angles are split, 3 in one broad region, Ammonite almost opposite. But when you rewind the orbits back to around 4.2 billion years ago, something sharp appears. The simulations showed their longitudes of perihelion bunching together, forming a tight cluster. Then you test how likely that is to happen by chance. You don't just run one simulation, you run many with slightly varied initial conditions, and you build up statistics. The result? There is more than 97% confidence that this clustering is real, not some random coincidence. That's not 100%, but in orbital dynamics, 97% is a loud alarm. So you're left with a strong statement. The four sednoids probably shared a tight alignment in their perihelion directions about 4.2 billion years ago, and since then, their orbits have slowly precessed and spread out to the pattern we see now. Ammonite, sitting on the opposite side today, is exactly what you'd expect from that long-term drift. Then you bring Planet 9 back into the picture, and things get more constrained and more awkward. When you insert a hypothetical Planet 9 into these n-body simulations, you can't just put it anywhere you want. If you place it too close or on the wrong orbit, the interactions with Ammonite over billions of years will destabilize Ammonite's path. It might get scattered, its perihelion might drop, or it might get ejected. The fact that Ammonite exists on a stable sednoid orbit right now means those destructive outcomes are off the table. So you scan Planet 9 paradigm space, different semi-major axes, eccentricities, inclinations, masses, and you ask a hard question. For which Planet 9 orbits does Ammonite stay stable over gigayears?
The answer squeezes the options. Only certain Planet 9 configurations work. They tend to push the hypothetical planet's semi-major axis outward, toward something like 500 AU or more, and into narrower bands of allowed eccentricity and tilt. That moves Planet 9 deeper into hard-to-ever-see territory. You can still keep the planet in the model, but now it's not a free idea. It's boxed in by Ammonite's survival. And through all of this, you have to remember, these simulations are not perfect movies of the actual past. They're ensembles. You're throwing a cloud of slightly different starting conditions into the equations, evolving them, and seeing what patterns show up again and again. You will never know the exact path Ammonite took 4.1 billion years ago on a specific date. What you can know is the statistical structure, that its orbit is long-term stable, that the four sednoids likely had a tightly aligned set of perihelia around 4.2 billion years ago, that the chance of that being pure noise is low, and that certain stories, like a close, easy Planet 9, are getting squeezed very hard by the requirement that Ammonite survives. So you end up with a simple but heavy conclusion. The outer solar system is chaotic, but not random. The sednoids are not noise. They are a coded message, and Ammonite is the newest, sharpest piece of that code. Which naturally leads to the next step. If these four objects carry that much information, how do they compare one by one? What do their orbits, sizes, and surfaces look like side by side? And what does that lineup say about the hidden population behind them? What happens when you finally line up all four sednoids and look them straight in the face? Let's put the numbers on the table, no fluff. Sedna first. Semi-major axis, about 506 astronomical units. Perihelion, around 76 AU. Orbital period, roughly 11,400 years. This is the heavyweight, the deep outer world champion. It swings way out, almost to 1,000 AU at aphelion. 2012 VP113 next. Semi-major axis, about 262 AU. Perihelion, around 80.5 AU. Period, roughly 4,200 years. Not as huge an orbit as Sedna, but with an even higher perihelion. It never comes close to Neptune, fully detached. Leleākūhonua, 2015 TG387, is the extreme case. Semi-major axis around 1090 AU, perihelion about 65 AU, orbital period around 41,200 years. That is ridiculous. It spends almost all of its existence in deep, dark space far beyond anything we can see directly. We just caught it because it happened to be near its closest point. And then Ammonite. Semi-major axis around 252 AU, perihelion about 65.9 AU, orbital period about 3,998 years. So in terms of distance and timescale, Ammonite is actually closest to 2012 VP113. Similar semi-major axis, similar orbital period, perihelion in the same high 60s to 80-ish AU zone. Right away, you see the pattern. All four have perihelia above 65 AU. All have huge semi-major axes, from a few hundred up to more than 1,000 AU. All have periods measured in thousands or tens of thousands of years. None of them come inside Neptune's region. They're all purely detached. Now focus on orientation. This is where Ammonite breaks rank. The first three, Sedna, 2012 VP113, and Leleākūhonua, share clustered orbital orientations. Their longitudes of perihelion all sit in roughly the same broad sector of space. That's the original weirdness that pushed people toward Planet 9. 3 independent discoveries, similar dynamical class, same directional cluster. Then, Ammonite arrives with a perihelion direction around 271 degrees, essentially anti-aligned with that cluster. Dynamically, it still fits the sednoid criteria. Geometrically, it refuses to point where the others point. But outside of that key angle, they're not random at all. Their inclinations, how much their orbits are tilted relative to the main planet plane, are all in the same ballpark, roughly 11 to 25 degrees. None of them are flipped upside down or tilted at 90 degrees. They're all modestly inclined, forming a coherent family in 3D space. It's not like Ammonite is some wild polar orbit outsider. It's aligned enough to be clearly part of the same dynamical story, just rotated in perihelion direction. Then you look at physical size and surface. Sedna is the giant of the group, probably around 1,000 kilometers across. That's unambiguous dwarf planet territory. It's big enough to be round, to hold on to volatile ices, and to have a complex thermal history. 2012 VP113 is smaller, around 450 kilometers across. Still a serious body, not a fragment, not a pebble. It's in that mid-range where gravity is strong enough to shape it, but it's not a major world.
Leleākūhonua is estimated at about 220 kilometers. That's on the small end of the set, more in the large icy body range, but still significant. Ammonite slots right into that mid-band, somewhere between about 220 and 380 kilometers, depending on assumed albedo. So again, not an outlier. It fits nicely into the size distribution. Surface-wise, Sedna is very red, deeply processed, coated in tholins and other complex organics. It's one of the reddest bodies in the solar system. 2012 VP113 and Leleākūhonua are also on the red side, consistent with long-term radiation processing of outer solar system ices. Ammonite comes in as moderately red. Its color indices fit right in with many trans-Neptunian objects and are fully compatible with a tholin-rich processed surface. It does not stand out as blue, gray, or neutral. So once again, it's not breaking the pattern here. It looks like a normal member of the same class. So, distances match, perihelia match the high detached regime, inclinations are similar, sizes are in a logical range, surfaces are all red flavored, 3 of them share clustered perihelion directions, 1, Ammonite, is flipped. You can't look at that and say, these are random. They are clearly a group, but a group with one internal tension point. Now ask how we even got this sample. Did we sweep the whole sky carefully and find 4 out of millions? No, the reality is worse. All 4 sednoids were discovered by wide-field, deep imaging surveys, pushing their hardware to the limit, not from casual pointings. And in every case, they were found when they were near perihelion, the one part of their orbits where they get bright enough to show up in our data at all. That means we are catastrophically biased toward the tiny fraction of sednoids that just so happen to be 1, near perihelion right now, 2, large enough and reflective enough to be seen, and 3, in the patches of sky our surveys actually covered.
Most of the time, Sedna is nowhere near where we see it now. It's way farther out, much fainter, impossible to detect. The same goes for Leleākūhonua, 2012 VP113, and Ammonite. At any random moment in time, most sednoids would be near aphelion or somewhere far from perihelion, and therefore totally invisible to our current telescopes. So what we're seeing is the absolute tip of the iceberg, 4 objects that happen to line up with our observing windows at the brightest segments of their orbits. If that's all we get out of limited surveys, the true underlying population almost has to be huge. And this is where the story goes from data table to crime scene. Picture it like this: 4 specialists with similar backgrounds and one with a slightly different move. Sedna, the big boss on the widest orbit. 2012 VP113, the tight, high perihelion operator. Leleākūhonua, the deep cover agent living almost entirely in the dark. And Ammonite, the one whose orbit orientation doesn't match the others, the rebel that exposes the flaw in the simple Planet 9 story. They all come from the same neighborhood, the distant, detached fringe beyond Neptune. They all carry scars in their orbits that point back to something violent that went down about 4.2 billion years ago. And they all tell you, in different ways, that our current map of the solar system is missing major pieces. The lineup is not comforting. It's a warning. If just 4 sednoids can force us to rethink the architecture, what will happen when we start finding dozens, hundreds? And that leads directly into the next pressure point. If 4 sednoids already imply a massive unseen population, what does Ammonite specifically tell us about that missing crowd? The millions of objects we haven't seen yet, but that absolutely must be there if this fossil record is real. How many worlds are we missing if something as extreme as Ammonite can just fall out of the data in 2025? Let's start with the brutal math problem: rarity versus reality. We have 4 sednoids, not 4,000, 4. All of them were found in limited surveys with limited sky coverage over limited time windows using hardware that is only just good enough to see them near perihelion. When you run survey simulations and factor in how tiny the detection window really is, you don't get, oh, there must be 5 or 10 more out there. You get numbers in the thousands or millions. Leleākūhonua's discovery already pushed people to those crazy counts.
Some models suggest there could be more than 2 million inner Oort Cloud objects larger than about 40 kilometers in diameter. Not 4, not 40, millions, with a combined mass somewhere around Pluto's. Ammonite's existence supports that because it fits the same pattern, a rare, caught-in-the-act object that we only see because it happens to be near its closest point to the sun right now. If 4 such objects show up under all these constraints, the underlying population cannot be small. The only way that works is if the background is huge and we're only seeing the brightest, nearest scraps. Now look at how biased we are. Our telescopes are not scanning the whole sky equally all the time to infinity. They have limits. We are mainly sensitive to objects that are 1. Near perihelion, where they are closest to the sun and therefore brightest, 2. Not too small, or they're just too faint outright, and 3. Not too dark. A low albedo object reflects very little light and disappears into the noise. Ammonite's detection tells you it hits the sweet spot. Near perihelion, size of a few hundred kilometers, moderate albedo, and in fields that our surveys actually covered. If Ammonite were half as big or darker or slightly farther along in its orbit, we would not have seen it. It would be completely invisible right now. That means there is an entire parameter space, smaller, darker, slightly farther, filled with objects that our current instruments simply don't touch. So every time you hear, "We found a new sednoid," read it as, "We barely scraped another grain off a mountain we can't see." Ammonite doesn't just add one more case, it screams how incomplete our census is. Now go deeper. These aren't just bodies, they're records. Their orbits are data. Each orbit encodes multiple things at once: where the object likely formed originally, how strongly it was scattered by giant planets or rogue planets, how much its perihelion has been lifted by galactic tides, what stellar passes it might have felt, and how long it has been detached from Neptune. Ammonite's high perihelion, mid-range semi-major axis, anti-aligned perihelion direction today, and reconstructed alignment 4.2 billion years ago all carry pieces of that story. Same for Sedna, 2012 VP113, and Leleākūhonua, each in their own way. With 4 sednoids, we can already say something strong hit the outer solar system early, the orbits were clustered, the cluster has been spreading, and the population is large. But with just 4 objects, you can't fully reconstruct the environment. You can argue about whether it was a rogue planet, a close stellar flyby, capture from another star's disk, or some hybrid scenario. With dozens of sednoids, that changes. The distribution of their perihelions, semi-major axes, inclinations, and longitudes of perihelion would let you reverse engineer the early system. You could tell whether the sun almost certainly formed in a dense cluster. You could test whether rogue planets had to exist. You could see whether the inner Oort cloud is mainly built by stellar encounters or by long-term interactions with exoplanets. Ammonite is one more piece in that dynamical fossil record. Not enough to fully decode the message, but absolutely enough to tighten the range of allowed histories. And this leads to a different way of thinking about planet hunting. We usually picture planet searches as looking directly for planets, tracking wobbles and stars, dips in brightness, faint moving dots. But out here beyond 60 AU, that's almost impossible right now. Planet 9, if it exists, would be near the detection limit even for major telescopes. So instead, we're doing a new kind of census. We're counting the scars left by planets and other perturbers. Detached objects like the sednoids are those scars. Inner Oort cloud bodies are those scars. Their orbits are the traces of massive things we may never see directly. Lost planets, passing stars, the galaxy's slow grip. Each new detached object is not just another rock. It's a measurement of the invisible forces that shaped it. Ammonite is exactly that. One extra hard data point on the plot. It doesn't announce, "Here is Planet 9." It says, "Whatever sculpted us, here's another constraint."
It tightens the error bars on every model that tries to explain the outer solar system. It makes certain Planet 9 orbits less likely. It makes certain early stellar flyby scenarios more plausible. It raises the required size of the unseen population in the inner Oort cloud. And it leaves us with a blunt conclusion. If we want to stop guessing and start measuring the missing population properly, we need a new wave of surveys powerful enough to find many more Ammonites.
That's the next step in this story, the hardware that's coming. Rubin, Roman, and the next generation of big telescopes, and how they will turn four freak objects into the first real map of the hidden outer solar system. What happens when the next generation of telescopes turns the whole sky into a continuous surveillance feed for faint, slow objects? Right now, sednoids are rare because our tools are weak. That's about to change. The Vera C. Rubin Observatory is basically a sednoid trap waiting to be switched on. Its main project, the Legacy Survey of Space and Time, LSST, will scan the southern sky again and again for a full decade, using an 8.4-meter mirror and a 3.2 gigapixel camera. That isn't take a picture, move on. That's the same fields revisited hundreds of times over 10 years. Every visit adds more photons. Every revisit adds more motion information. For something like Ammonite's cousins, faint, slow, and at 50 to 1,000 astronomical units, this is exactly what you need. You're building up a massive time-lapse of the sky, frame by frame, night after night. Rubin is designed for a lot of things: supernovas, dark matter, veritable stars. But as a side effect, it's almost purpose-built to nail distant trans-Neptunian objects. Slow drifters that were invisible in old surveys will leave clean, trackable trails in LSST stacked data. What took insane effort for one Ammonite-level object now becomes part of a standard pipeline. And that's where the software jumps in. Shift and stack is not going to stay at the level it was for fossil. It's going to get meaner. With LSST scale data, you don't just eyeball motions, you deploy smarter algorithms specifically tuned for outer solar system distances. You know what parallax and orbital speeds look like at 50 AU, 200 AU, 1000 AU. You build search grids over those motion ranges and apply targeted shift and stack along those paths. Instead of blindly testing random motion vectors, you aim at the dynamical sweet spots. Show me everything moving like a body at 70 AU. Show me candidates that match 300 AU motion. You let the code dig deep into the noise where individual exposures show nothing, but tens or hundreds of aligned frames reveal a real object. This isn't just better software, it's a new regime. The same way we moved from looking at plates by eye to automated asteroid surveys, we're about to move from one-off sednoid hunts to industrial-scale outer solar system searches. Once Rubin is fully ramped up with optimized shift and stack, single Ammonite-level discoveries won't be the story. The story will be, here are 20 more sednoid candidates from this season alone. But finding the orbit is only the first stage. We don't just want positions, we want composition. Once LSST and other Whitefield surveys start spitting out candidates, the big guns come in. Keck, the Very Large Telescope, and future giants like the Giant Magellan Telescope and the 30-meter telescope. These are the machines that can do spectroscopy on stupidly faint targets. You point one of those at a sednoid candidate and collect as much light as possible. You spread that light into a spectrum and look for absorption features. Methane ice, nitrogen, water, methanol, complex organics. You measure colors precisely. Maybe with thermal infrared, you even get some handle on their temperatures and sizes independent of albedo. That's when the game changes from orbit fossils to chemical fossils. Instead of just saying, this thing's orbit was shaped by a violent event, you can say, this thing's surface chemistry looks like it formed closer in and was thrown outward, or this one has a composition more like classic scattered disk objects, or this one looks alien compared to the others. Orbit plus chemistry is a much sharper weapon. With a dozen sednoids and decent spectra, you can start separating different origin stories. Which ones likely came from the inner Kuiper belt, which ones match captures from another star's disk, which ones show evidence of thermal processing early on. Ammonite is the first step toward that regime. It's the signal screaming, get me spectra while you still can. And then there's the idea that sounds insane now, but is absolutely going to sit on serious slides in serious meetings. Sending a spacecraft out there. A mission to the inner Oort Cloud is not a casual project. You're talking about tens of kilometers per second in cruise velocity, multi-decade flight times, unforgiving power and communication limits, and a target that barely reflects sunlight. It's hard on every front: propulsion, navigation, operations, instruments. But concept studies exist. People have already started sketching trajectories that use Jupiter or even solar orbit maneuvers, dipping close to the sun and burning hard to fling a probe outward with enough speed to reach 100, 200, 300 AU within a human lifetime. Add next-generation propulsion ideals, advanced electric propulsion, nuclear thermal or nuclear electric concepts, and the insane start shifting towards brutally difficult but not impossible. Here's where Ammonite and friends matter directly. As long as the inner Oort Cloud is just a theoretical reservoir, missions to it sound like sci-fi fluff. Once you start naming specific objects with real orbits, real colors, real physical estimates, the conversation changes. You're no longer talking about sending a spacecraft to nowhere. You're talking about sending a spacecraft to Ammonite, discovered in 2023, orbiting between 66 and 438 AU, with a 4,000-year period and a moderately red processed surface. That is how science fiction turns into engineering. You get a target, you attach a name, you attach a clear science case. This object holds fossil information about a violent event 4.2 billion years ago that reset the architecture of our solar system. That's the kind of line that ends up in mission proposals. So the roadmap looks like this. Rubin and LSST flood us with candidates. Smarter shift and stack pull sednoids and inner Oort Cloud bodies out of the data at scale. Big telescopes follow up with spectra and colors, turning orbital fossils into chemical fossils. And in the long term, one of those worlds, maybe Ammonite, maybe something even stranger we haven't found yet, becomes the anchor for the first mission beyond the Kuiper Belt into the true deep outskirts. The tension here is simple. The hardware to blow this field open is almost ready, but the window for objects like Ammonite to being easy targets is closing as they drift away from perihelion. We're racing our own technological curve against their slow, relentless motion outward. Which sets up the next question perfectly. Even with all this tech, what about you? Can anyone outside the professional world ever see Ammonite at all? Or is this one of those discoveries locked behind giant mirrors and supercomputers? How do you connect to a world you will never actually see with your own eyes? Let's be blunt about the visibility problem. Ammonite sits at an apparent magnitude of about 25.4. If that number doesn't mean much yet, here's the scale in simple terms. Under a dark sky, your naked eye can reach maybe magnitude 6. That's the faintest star you can pick out by eye. A big, serious amateur telescope, under great conditions, can visually reach maybe magnitude 15, 17. If you do long exposure astrophotography with a good setup, you might push deeper than that on images, but visually, you're done by the high teens. Magnitude 25.4 is not a bit fainter. It is orders of magnitude fainter. Each 5 magnitudes is a factor of 100 in brightness. Going from 15 to 25 is 10 magnitudes. That's 100 times 100 equals 10,000 times dimmer. Compared to the eye's limit, we're talking millions of times fainter. This is the regime where every single photon counts. Literally. Miss a handful of photons, and the object disappears into noise. At that brightness, you need huge mirrors. You need long exposures. You need cooled CCDs with very low noise. And you need the best sky conditions on Earth. And even then, you don't get a nice dot popping out of the frame. You get a tiny statistical excess that only shows up after stacking and processing. So no, you will never walk outside, look up and say, hey, that faint star is Ammonite. That will never happen for any human ever. That's the first hard truth. Second truth, even in the big telescopes, this thing is only briefly good. At the time of its discovery, Ammonite was about 71 astronomical units from the sun. It was on the way in toward its perihelion, which is expected around February 2063. That's when it will be at its closest, roughly 66 AU. That is as bright as it ever gets in its 4,000-year orbit, and even then, it's at magnitude 25. So the next few decades are the peak window. Brightest here still means ridiculous, beyond the reach of amateurs, barely within the grasp of large professional facilities.
After it passes perihelion and begins to move outward again, the brightness drops, slowly at first, then relentlessly. Over the next centuries and millennia, it will fade to the point where even most pro telescopes won't have a shot. For the vast majority of its orbital path, Ammonite is effectively invisible to us. We caught it in the one tiny stretch of its orbit when it's technically observable. That should make it feel less like a cool fact and more like a warning. You live in the only couple of centuries where this object can be studied at all. So, what does that mean for you? Practically, with a backyard telescope or even just curiosity? Let's be honest, you are not putting Ammonite on your targets for Saturday night list. No amount of aperture upgrades or clever filters will change that. The object is simply outside the lane of amateur observing. If you try to point at its coordinates, all you will see is a star field. The thing you came for is buried far below your detection threshold. But that doesn't lock you out of the discovery. You can still see Ammonite, just not as light in your eyepiece. You see it in real survey frames, deep stacked images where the team has highlighted the faint moving pixel that marks its position. You see it in orbit diagrams, plots showing the sun, the planets, the Kuiper belt, and then this long, skinny loop sweeping out into the dark. You see it in simulations, animations of the four sednoids evolving together over billions of years, their orbits clustering and then drifting apart. This is how we truly observe Ammonite, through data products, not through direct casual viewing. The story lives in graphs, in curves, in numbers. That sounds dry, but that's where the power is. The orbit is the message. The light is just how we extract it. And that leads to the deeper question. Why care so much about something you can never see directly, that will never be a beautiful eyepiece object or a pretty astrophoto? Because the hardest things to see are now the most informative. We have found all the big, obvious planets. Mercury through Neptune, done. Dwarf planets in the Kuiper belt, dozens known, hundreds inferred. Big moons, mapped. Major asteroids, cataloged. The bright and easy phase of solar system discovery is over. The frontier has moved into objects like Ammonite, faint, distant, dynamically extreme. These worlds don't impress you with pictures. They hit you with what their orbits say about the entire architecture. Each one is a test of our models. Each one is a constraint on whether Planet 9 exists, whether we had rogue planets, whether the sun was heavily disturbed by passing stars. Ammonite is valuable precisely because it's so hard to see. The fact that we needed decades of data, top-tier telescopes, and heavy computation just to confirm it means we are operating at the edge of what our current technology can do. That edge is exactly where the deep structural secrets of the solar system live now. So no, you will never aim a backyard scope and personally bag Ammonite. But you can do something better. You can understand why this almost invisible object forces professionals to admit that the map of the solar system is not finished, and that our pretty textbook diagram is missing entire populations and possibly entire planets. And that brings us to the last sharp turn of this story. If Ammonite is a fossil world that we can barely see once in 4,000 years, what does that say about us, about the timing of our civilization, about the fragility of our neat solar system story, and about the fact that we happen to show up right when the universe finally lets us read this layer of its history? What if the most important fossil in our solar system isn't a rock you can hold, but a set of orbital numbers on a screen? The nickname Ammonite is not cute branding, it's precise. On Earth, paleontologists read history in Ammonite shells, tiny ridges and spirals that record oceans, extinctions, shifts in climate over hundreds of millions of years. Out here, planetary scientists do the same thing, but the shell is in orbit. Ammonite is a shell in the dark. Its fossil isn't a spiral of calcium. It's a 4,000-year orbit with a perihelion at 65.9 AU, a semi-major axis of about 252 AU, an eccentricity of 0.74, and a longitude of perihelion flipped into opposition with the earlier sednoids.
That curve of numbers encodes where the sun likely formed, in a crowded cluster, not in isolation. It encodes that there were powerful perturbers out there, rogue planets, passing stars, or both. It encodes that the solar system survived a phase of chaos more violent than the neat textbook diagram ever admitted. You're not looking at just another icy world. You're looking at hard evidence that the solar system has a buried past. And that hits the next point hard. Our map is fragile. For over a century, the story we told was simple. Sun at the center, 8 planets in predictable order, then a belt of leftovers, the Kuiper belt, out to around 50 AU. Beyond that, a distant spherical comet reservoir, the Oort Cloud, way out at tens of thousands of AU. Clean, layered, easy to draw on a classroom wall. Sedna cracked that story. 2012 VP113 widened that crack. Leleākūhonua opened it further. Ammonite pushes it near breaking.
These orbits say there is not just Kuiper belt, then big empty, then Oort Cloud. There is structure in between. There are hidden populations, inner Oort Cloud bodies, detached objects, sednoids that we barely sample. There are hidden perturbers, massive things that used to be here or are still here that we haven't directly seen. There might be lost planets that were rejected. There might be a planet 9 on a distant extreme orbit. There might be signatures of passing stars etched into these trajectories. The solar system is not a tidy onion. It's a crime scene with missing files. Ammonite is one of the few pieces of evidence we have, and it's enough to say the old map is incomplete, maybe fundamentally wrong in how it treats the outer regions as just a cloud. And here's the part where it gets personal. We live in a ridiculous, lucky sliver of time. Think about the conditions that have to line up for you to even know Ammonite exists. First, you need telescopes powerful enough to see an object at 70 plus AU at magnitude 25. That means giant mirrors, sensitive detectors, and global-scale observatories. That's the last few decades, nothing more. Second, you need the specific object to happen to be near perihelion during the tiny window when you have that technology. Ammonite's orbital period is about 3,998 years. It's bright enough for real study for maybe a century or two around perihelion. That's a tiny slice of a 4,000-year orbit. If human civilization had risen 1,000 years earlier or later, we would have missed it. Third, you need computers powerful enough to take that orbit, plug it into n-body codes with other planets, and rewind it 4.5 billion years with realistic physics. That's not a 19th century task. That's modern, high-performance computing. We're talking about the last couple of decades again. Stack those conditions. Powerful telescopes exist, Ammonite is at the right place in its orbit, and we have enough computing to run billions of years of simulations. All three at once, only now. You, me, everyone alive, we exist during the rare, narrow window where a sednoid like Ammonite can be discovered, characterized, and used to interrogate the entire early history of the solar system. If human history was shifted by a few hundred years either way, Ammonite would still be out there. Its orbit would still be there. The record of the rogue planet, the stellar flyby, the inner Oort Cloud population, all of that would still exist, but no one would have the instruments to see it or the computing power to decode it. The fossil would be unread. Instead, we landed in the tiny overlap where the fossil and the tools coexist. So where does that leave us? With a final, uncomfortable upgrade of the original story. We used to say, we live in a solar system with 8 planets, a belt of debris, and a distant cloud of comets. That's the children's version. The real version, the one Ammonite forces us into, sounds more like, we live in a system that was hammered by rogue planets and passing stars, that hides millions of unseen icy worlds in an inner Oort cloud we can barely sample, and that may or may not still host a distant giant planet we haven't managed to detect. We have 4 sednoids as hard evidence of that violence. One of them, Ammonite, proves the story is still incomplete. And that is not the end. It's the beginning. Because Ammonite isn't the finale of the story, it's the first clear sentence in a language we're just starting to read. The language of the inner Oort Cloud, written in orbits, inclinations, and perihelion angles instead of words.
The next time a Rubin image or some deep survey frame shows a tiny moving pixel at the edge of the data, the stakes will be higher. That pixel might be another sednoid. It might tighten the noose around Planet 9. It might favor the rogue planet ejection scenario. It might support the stellar flyby model. It might reveal a completely new pattern we haven't even thought to look for yet. But here's the real tension. At some point, one of these pixels will do what Ammonite did and more. It won't just be another member of the family. It will be the one that finally forces everyone to admit exactly how the outer solar system was put together, and what kind of chaos is normal for planetary systems across the galaxy. So you went here, but with the door open. Ammonite is not the end of the story. It's the first clear sentence in a new chapter. The next time a survey finds a tiny moving pixel at the edge of the frame, we might not just be adding another fossil world to a list. We might be staring at the missing chapter in how our solar system, and maybe planetary systems everywhere, are actually born. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.